So the way this is set up in a monochromator, this is a specific style of monochromator known as a Cherney-Turner monochromator. There are different ways of arranging the optical components, but this is a very common one. And the idea here is we have an entrance slit, which collimates the light, which means that we get our light going a specific direction. So, if we have a very, wide angle of light coming out here, we just pick one particular beam that's going through our entrance slit. And that allows us to control where it goes in the rest of the monochromator. So the light from the monochromator bounces off of a mirror and gets focused onto a diffraction grating. And so the diffraction grating will get different colors of light coming off at different angles. And we can change which colors of light are going which direction by changing the angle of the grating. And so the light from the grating is sent to another mirror, which will focus the light onto what's known as the focal plane, where we have another slit, this exit slit. So one wavelength will go through the slit, but a different wavelength here, lambda 1, for example, will just hit the side of the slit and not make it through the monochromator. And that's how we pick a specific color of light, is with this exit slit. Now, the exit slit provides a trade-off, which is common in many analytical instruments, that we can improve performance but add some disadvantage. And so our trade-off here is that a narrow slit lets through a smaller range of wavelengths, right? So we'll get whatever wavelengths can fit through this gap, we'll make it into our detector where we can see the light. And so there's a certain width in nanometers of wavelengths that'll make it through. And if we have really closely spaced peaks, we won't be able to resolve them very well. And we'll look at that on the next slide in more detail. But it will get more light through, which will give us more signal on our detector. And on the contrary, if we have a narrow slit, we can pick a smaller range of wavelengths, but we have less light on the detector, smaller signal. But if we have a wider slit, we can get more signal through. Higher signal noise ratio is better in terms of measurements, but we have a wider range of wavelengths, which means we have a worse ability to resolve peaks. So this is a trade-off that we have to make with the exit slit of a monochromator. We have to pick if we need the resolution, then we lose some amount of light, which makes the signal noise worse. So related to that idea of the resolution of the exit slit, let's talk about that in some specifics here. Why this matters is that we're often measuring multiple peaks in an absorption spectrum. And what we'll see depends on the bandwidth of the monochromator, meaning the range of wavelengths that will make it through our monochromator. So if we have a very wide range of wavelengths that can make it through, say, monochromator bandwidth, and what we can measure this in is in terms of nanometers, saying like 448 to 450 nanometers will make it through a monochromator, or in this case 606, right, to 608 or something like that. We'll see when we measure at low resolution, we see there's actually 3 separate peaks here, 1, 2, 3. But if we have a very low resolution, all those peaks smear together and it looks like there's only one peak that's present. And so if, say one of these peaks is from our analyte and something else is from an interfering species, we wouldn't be able to distinguish that at the low resolution. But high resolution, we can get a much clearer sense of where the peaks are and see the individual peaks. And so this is a combination of both that exit slit as well as the diffraction grating itself. And so there's an equation that describes the resolution that you can get with the diffraction grating. And so that is given here. And the wavelength over the difference in wavelength for our peaks, that's what we consider our resolution. And that's equal to our diffraction order. So it depends, which order we're using affects our resolution that we have, times the number of grooves illuminated. So on our diffraction grating, for a certain length, this is the number of grooves that'll be illuminated depending on how we have our instrument set up. So you get a chance in the homework, you'll have a question or two related to this equation where you'll get to use it and see how many grooves per millimeter you need for a specific application or things like that.